Okay, cool. So yeah, we're going to take a little bit of a twist here and talk about learning to generate shapes. And actually, program synthesis is a super relevant sort of lead-in for this. And I'm going to talk about some of the work that's just generally happening in the research world, and also just some of the work we've been doing inside of Autodesk Research in the AI lab. So for those of you who are not familiar with Autodesk, you may be familiar with some of the things that are made in our software. So if you've driven a Tesla, or own a Tesla, or own a skyscraper, or have been to Mars, you may have seen some of the things that have been made in our software. And so we make design and make software, and it goes from the architecture industry to manufacturing to media and entertainment. So one of the challenges we have is you can kind of imagine the data that we have to deal with, right? And it's pretty challenging. So first of all, it's really high dimensional. So if you look around this room, imagine all the lights, imagine all the wiring, imagine all the gas, the electricity, all those things have to be modeled in 3D software. And that's, yeah, a little bit more complicated than just dealing with kind of Cartesian data, right? So rather than rows of pixels, we have this multiple dimensions of data that doesn't align to a specific grid. Also, because it's design, and design is made by people, it has a high variance, right? So people design things in different ways. My dream car is probably different from yours, and there's just all sorts of things that happen in the design world that are wild and wonderful. And also labeling, right? So because it's design data, typically when we have things labeled, we have to have them labeled by experts. So whether they're mechanical engineers or architects, it's a little bit more complicated than just, is this a cat or is this a dog? So this is some of the challenges we deal with. And why do we want to generate shapes? And I just want to give it like a simple example. So you're, I think, all familiar with text autocomplete. So when we type in the browser something like is Autodesk Research, it comes back with worth it, is Autodesk Research good or legit? And I assure you it is. And we want to do something similar with design. So imagine if we had a design tool where we could begin to input some of the pieces. Oops, well, that video didn't play. But we want to be able to autocomplete that sequence of operations, so the modeling operations that people do. And so one of the starting points is dealing with 2D vector shape generation. And so I think everyone's super familiar with images, and there's been like a lot of work done with images. But a lot of the stuff that we deal with, looking back, some time ago, is dealing with creating vector representations, things like floor plans, right? So this is what it used to look like, designing a floor plan, and it just happens that the data that people still work with when they represent buildings or when they represent mechanical structures, or even fonts or even icons, it also has this vector representation. And that's really, really helpful because it's really easy to be able to make quick edits and change things. You're not sort of needing to get down there on the pixel level and move things around. So it's really, really useful when you're making fast design changes. And so one of the challenges that comes along with having this vector representation compared to something like images, right, like raster representation, is we no longer have this nice pixel grid, which we can use things like convolutional neural networks to create these nice local features and then solve things like classification. So we're essentially dealing with this 1D sequence of tokens, right, which is a series of curve commands, so one after the other saying draw a line, draw an arc, draw a circle, et cetera, et cetera. And each one of those curves has a set number of parameters that go along with it. So I want to just sort of show some of the work that's been going on in the research community on this area. And I think I'll start with a little bit of a Turing test here. So these are 4 different fonts. One of them is made by a human, and the other 3 are generated by machine learning models. Does anyone want to guess which one was made by a human? Yes, the bottom one, right? So sort of sums it up, right? We're not quite there, but we're getting close. So these are papers from NeurIPS, from SIGGRAPH, from CBPR. So they're legitimate research. And you can kind of see, right? Like we're getting kind of closer and closer as the years go by to getting towards generating like fonts, right? So this will be an exciting future when we have an automatic font generator. But if you kind of take a closer look, right? you can see there's some differences in the approach. So I want to talk about like from left to right. So deep SVG, the shape is not really well matched to the ground truth human design on the right. But you can see that the actual topology, so the curves that are used and the amount of curves is actually pretty good, right? And this is because they train on that vector supervision. So basically, like they train on how humans have created fonts. And so like even though the sort of accuracy is not that good, but it's actually like a good topological solution. An image to vec is a different solution that uses raster supervision. And what you see is that they get really, really close to the shape, but then the number of curves is just like way more than a human would choose to do. And then the last one, deep vec font, they kind of combine, right, both of these approaches of supervision from a vector source as a raster source. And what you see is this sort of combination really gets you the closest to what a human would design. And again, this goes back to that idea of like what would happen if you wanted to go in there and actually make changes to this font in design software. And once you can kind of figure that out, you have this nice latent space, and then all the things in red are generated, generative fonts, right? So it's kind of gives you some nice capabilities to sort of interpolate between different font designs as you imagine if you're a font designer. So here's another one for the emoji fans. So on the left-hand side, it's the human design. On the right-hand side is the generated emoji. And they look, pretty close, a little bit rough on the right. But then you sort of click on this and look at like the actual structure of the data, and you see there's a little bit of a difference, right? So, and this kind of begs the question of how do people actually design things? And one of the characteristics, I think, of how people design is really to create like a minimal set of information by which we can make this sort of these high level edits, right? So we want to be able to go in there and with as fewer actions as possible, change the size of a circle or change, not having to sort of go in there and move like 10 different points to make that change. And we also just naturally, right, we naturally sort of align things. So concentricity is one thing, right? So that green circle is aligned like, in the center of the blue arc. And there's other things like coincident points, right? We have points that we want to snap together. We have like symmetry. We want like the heart on Valentine's Day yesterday to be symmetrical. Orthogonal lines, tangent curves. These are all kind of things that are hallmarks of human design. And I think ideally we want to be able to learn from that information because it's really, really helpful. And these are actually encoded explicitly in our software, right? So when we have a thing called engineering sketches, we actually have constraints that are applied to those sketches when we design them, and I'll show you sort of what that looks like. So here, this is an example of our Fusion 360 software, but basically like you're inputting these different dimensions which specify the lengths of a part of the design, and you can change them bit by bit, and dynamically the design has changed, the engineering sketch has changed to basically reflect the original intent. And to look at another example, so when you have these constraints applied, if you make these changes to the dimensions, the shape ends up going through the sketch solver and basically being the same type of shape that you originally inputted. But when you don't have these constraints set up, it ends up being quite different, right? So it literally takes it literally and says, hey, we're going to change, you want to change one side? Sure, we'll change one side, and then the whole thing gets kind of lopsided. So this is, I think, what we call design intent, right? Like when somebody sets something up, we want it to be something like this, right? Where we have these high-level controls of hole size and width, and we want to be able to span across that breadth of design. And this makes it super easy to make changes and to be able to edit and create different CAD designs. And this is a paper from DeepMind from, I guess, a year and a half ago or so. And left side is the human ground truth data, and right side is the generative engineering sketches. And you can see it's actually getting really good. And I think one of the reasons is because these, unlike fonts or emoji, this is a very, very structured type of information where it's there's a lot of patterns that come from those constraints that are easier to learn. So this is super exciting, right, for me. And of course, it leads to the question of like, how do we take that further, right? 2D is one thing, but the world around us is 3D. And so we want to be able to generate 3D objects and have those actually made and into chairs and tables and things in the real world. And so this begs the question of what's the right representation to do that? And I think the first talk had some great sort of examples of like how point clouds and images are really relevant for some 3D problems. In our world, when you want to actually make very, very precise surfaces that need to, when you close the door in your car, it actually needs to close and not just hit the side. And we usually want to talk about solid models, and these are basically models that are used in the industry standard mechanical engineering field, and they're composed of parametric surfaces that are very, very precise. And the benefit of this, is you can make very, very quick edits. Is that going to play? Okay. Yeah, so you can make very, very quick edits and quickly sort of extrude things, join them together. You can also do things like export the drawings that are needed for manufacturing, or do cross-sectional analysis, simulation, all of those types of things that are needed. And the underlying representation is called a boundary representation because it's representing the boundary of that 3D shape. And it's actually composed of this interesting hierarchy of, first of all, having a series of curves that make up loops. And then those loops bound the surfaces that are underneath them, so a plane or a cylinder or a torus or a sphere. And so those are all essentially stitched together like my jacket or clothing. And we essentially want to make a generative model that can sew these edges, these lines, and these faces all together to generate 3D shapes. And this is a work that we just got into the Transaction of Machine Learning Research Journal. And so we present the first generative model that can actually do this using this boundary representation without any supervision from modeling operations. And so we start by predicting a series of vertices. So these are the 3D points in space. We then use a sort of a different network to then predict how those vertices connect together to form edges, and then how those edges connect together to form faces. So it's this hierarchy of going from points to lines to surfaces. So I won't go too much into the architecture, but just at a high level, we're basically predicting the vertices first. Then we point into that sort of list of vertices to say, hey, connect these lines together to make these loops. And then we point into the list of lines to say, hey, join these together to make a series of faces. And then hopefully when that's all done, they all join together nicely if we've predicted it correctly to create a solid model. And we have these nice animations of what it actually looks like. And it really is like beautiful sewing in 3D, isn't it? So this is one example. Is another example. Okay, interesting. So another approach, there's some weird bug going on in my slides, but another approach that you can take to this 3D generation problem is not actually sewing together the surface of a 3D object, but it's actually learning the sequence of commands that underlie it. And so what that partially occluded sequence of images at the bottom is showing is this sort of sequence that humans input when they're creating a design. Okay, and when you play that back in a CAD software, it, again, partially occluded, but it looks like this on the screen. You're essentially sort of doing these sketch and extrude operations one by one. And we created a data set called the Fusion 360 data set that has this sort of supervision underneath it, and that's available online. So one of the most recent works we've done in this area was ICML last year, and this is basically representing, it's called SketchGen, and it's representing sketches in a way where we basically break out the tokens into a series of topology tokens as well as geometry tokens, with the idea that we can separate out topology and geometry to have some interesting controls over how the network outputs the geometry. And when we represent this again in a similar way by having curves that form loops, that form faces, that then form extrusion operations, and we sort of build them up from the ground up. And of course, they all get reduced to this series of tokens that are then fed into the transformer architecture. So the tokens start. One of the interesting things we do here is break apart into different encoders for topology tokens and geometry tokens and extrude tokens. and use vector quantized code books as a way to basically have some interesting control. I won't kind of go into too much detail, but you can look at the paper. And at the end, what we get out is this construction sequence that we need a CAD engine basically to rerun those commands, and that'll give us the geometry coming out the back of it. So these are some of the sketch generation results. You can see the 2D results on the left. So again, like it's actually getting really, really close, I think, to what human design looks like. And then the 3D generation results are on the right. So I think interesting starting point. We're seeing some really, I think pretty solid looking simple shapes. But I think one of the challenges here is because it relies on this extra level of supervision from the kind of sequence of modeling operations, we need a much, I think, larger set of data to really be able to go into creating really complex shapes. So I'm going to wrap up now, and I just wanted to really talk about a couple of points that kind of motivate, I think, the work we're doing. And I think one is that editability and editable representations really matter, right? And the reason for this is because when we think about how we're going to interact with these learning-based systems or AI systems, we really want to have the output of them be something that humans can actually utilize and edit, make changes to, and then the AI can essentially take that in, create some other output, and then that loop can go around and around, right? I think even if you're 99% accuracy, that's wrong every once every 100 times, right? So we need a way to be able to build upon that and sort of have some kind of collaboration, right, with these systems. And that really matters for design. Designers, I think, are very, they have their own set of preferences and rules that, are hard to encode in a very general model. The other point I want to make is that design is a really critical part of, I think, everything that happens in the physical world. And there's just so many problems that I think can be improved by having better design tools. And you think of, what does it take to create net zero buildings that reduce the carbon output? What does it take to make, more fuel efficient vehicles? What does it take to have, better, more efficient factories? Like all of these problems kind of start from the point of having really good design. So that's what makes me excited about getting up in the morning and tackling some of these problems with ML. Thank you very much.